First of all, thanks a lot, Sveta, for inviting me. I already have 3 ideas that I want to pursue when I come back, so my students can't wait. I think at the beginning of every other talk, one has to say that he's not going to dance. So I'm not going to dance, but I would like to entertain you by showing quite a few movies demonstrating the ideas of surface plasma and polaritons interacting with aggregates of quantum objects. So here is a quick outline of my talk. I will talk about brief and quick overview of plasmonics, and even though several people talked about what plasmons are, I would like to show you how they look like in terms of near-field distributions and time dependence as well. So then we'll briefly discuss the ideas of merging classical electrodynamics with quantum simulations. That's the holy grail of our approach. Then we'll use this approach to discuss linear optics hybrid systems comprised of plasmonic structures and strongly coupled to arrays of quantum emitters such as quantum dots, G aggregates, and whatnot. And of course, the whole idea was to look at collective effects. So we do these simulations self-consistently, taking into account not only the interaction of quantum emitters with plasmonic fields, but also with themselves as well. And finally, I will show you a few brand new results that we got just like 10 days ago, and we're still in the process of trying to understand what's going on there. So these are nonlinear optical structure simulations of transient spectroscopy and some ideas of coherent control. Okay. So the first step to in all plasmonic talks is to tell you what I mean by plasmons. But every time someone is saying this is a plasmon, this person usually means something different. So, so what I mean when I say plasmon, I'm referring to really simple electromagnetic waves that are associated with collective oscillations of conductive electrons. So if you look at the very simple flat interface between non-dispersive dielectric on the top and some dispersive dielectric on the bottom with epsilon depending on frequency, that could be metal, for example, I can solve Maxwell's equations and find that there are several modes associated with this structure. One of them is the standard Brewster mode. If the real part of dielectric constant is greater than 0 at a given frequency, then all my waves that I'll get are propagating waves with solid lines indicating real k vectors. Now, and of course, this whole thing is not really confined in space, and since the small propagation constant leads to a long wavelength. Now, although at some particular frequency, some materials, especially noble metals, in the visible part of a spectrum, they exhibit negative epsilon. So if the real part of the epsilon becomes negative at a given frequency, then we'll have so-called propagating surface plasma and polaritons, and these guys basically can propagate along the interface, but exponentially decaying into dielectric or metal as well. Now, the interesting part is that they have a strong spatial localization because they have a large propagating constant and short wavelength. So they are oscillating at the given frequency of interest, but they are strongly localized in space. Now, let me show you a few examples of the surface plasma and polaritons. So one of them is a periodic array of slits. I will use this structure in simulations in a few minutes. Here I have a periodic array of slits, and I'm illuminating these slits with a plane wave that propagates from top to the bottom and oscillates from left to the right, and the frequency of surface plasmons. And what you see is that the field is strongly localized inside the slit, and the size of the slit is on the order of 100 nanometers or less, and the thickness is about 150 nanometers. And of course, depending on the time, you have a strong localization of the field and on the interface as well. Okay. Now these are the time intervals in femtoseconds, so it's pretty fast and strongly localized. Now, if you ask what the frequency of these oscillations is, is on the order of 3 point something electron volts. So it's a visible part of a spectrum. Now, another example is a periodic array of holes. It's easier to do experimentally, but harder to do in terms of simulations because of 3D. But nevertheless, these structures support several different surface plasmons. And one of them I would like to illustrate. If I put a detector really close to one of these holes and look at the electromagnetic radiation that comes through, what you will see is very strongly localized and nicely depending on time fields. And again, this is the frequency on the order of 2-something electron volts, and this is the time in femtoseconds, really, really fast. So we have a spatially localized electromagnetic fields on the femtosecond time scale.
What dielectric functions do you insert?
Yeah, that's a good question. So the epsilon is a function of frequency we use as a fitting function from Johnston and Christie. So these are real numbers from real experiments. Okay. Now, another example, so these are propagating surface plasmon polaritons. There is also a localized surface plasmon polariton associated with, let's say, nanoparticle. So here is the nanoparticle of silver with a diameter of 50 nanometers. And here's the scattering cross-section as a function of the incident wavelength. What you see is that the particle is very small, but the resonance is on the order of 100 nanometers. So if I illuminate this particle with the resonant light, what I'm going to see is a very strong localized field, again, oscillating and strongly localized in space on the interface. So here is a plane wave comes from left to the right and is vertically polarized. And again, this is the time in femtoseconds. And by the way, what I'm plotting here is the intensity, and it's a log scale, which means that the enhancement is really, really strong here. Could be on the order of 3-4 orders of magnitude. Okay. So highly spatial localized magnetic field is caused by collective oscillations of conductive electrons. And when I say plasmon, I'm referring to the oscillations of electromagnetic radiation associated with oscillations of collective conductive electrons. Yes?
What is the period again?
The period?
Yeah, is this a single particle?
No, this is the single particle in vacuum, yes. Okay. So to quickly summarize, we have collective excitation of conductive electrons, what I call the surface plasmons, and the electromagnetic field is localized in the interface between dielectric and metal. And for double metals, the resonant wavelength is indivisible, so highly sensitive to geometry incident field parameters. If I change the shape of the nanoparticle I showed you a few seconds ago, of course, the resonance moves depending on the size of the particle, depending on the shape as well. So it's a really nice adjusting parameter. And it leads to really high local electromagnetic fields. Okay, so now our main interest is to combine these kind of structures with quantum emitters and a strong coupling regime such that these emitters will strongly interact with the local fields and produce some interesting features. And our first goal is to look at what kind of theory one can develop to efficiently simulate the optical properties of these systems. So one of the motivations is our ongoing collaboration with the University of Sao Paulo, where they look at the near-field transmission of light with, through plasmonic material coupled to Tillery glass. And they see interesting features of strongly coupled regime when the surface plasmons interacting strongly with erbium ions in the Tillery glass. Another collaboration ongoing with Yehim Prior and Weizmann Institute, they look at the linear and nonlinear properties of J aggregates coupled to surface plasmons as well. So when I will say hybrid material, I will refer to material comprised of plasmonic material resonantly coupled to array of quantum emitters. Okay, so such as quantum dots, J aggregates, and so on. So coupling plasmons to molecular excitons, for example. So here is one of the first papers on these kind of structures published by Adi Salomon when she was a postdoc at Tom Ebbison Group several years ago. So I look at the periodic array of holes, and varying the period of this structure, you can adjust the transmission as a function of the wavelength, moving plasmon resonances from one position to another. So these are the various transmissions as a function of the wavelength at different periods. So you see you can move the plasmon resonance from one point to another. Now, depositing the thin layer of J aggregates on top of this structure, you can adjust the chemistry such that the absorption of these J aggregates will be right on top of the surface plasmon polariton, and since these J aggregates support really strong dipole moments in the visible part of the spectrum, you expect there will be strong optical coupling. And indeed, if they do that, they look at the transmission as a function of the wavelength, and you see the solid line is the hybrid system, and the resonance splits in two, so you have what is called a Rabi splitting. Okay, by looking at the Rabi splitting, you can see that this is on the order of 100 milli-electron volts, so the coupling is really, really strong. But of course, one doesn't need to have a strong, sophisticated theory to predict that. All you need is just a 2x2 matrix, diagonalize it, and you have avoided crossing. And these are the energies of these two modes as a function of the wave vector. You see a very nice avoided crossing feature, right? Now, in reality, what they've done in their experiment, they start cranking up the density of the J aggregates, and the splitting became bigger, 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 and bigger. And at some point, they observed the third spike that appeared right in the center, and they couldn't explain that. And of course, you have to have at least 3 by 3 matrix to explain that. So that's where we came in and tried to use our theory. Okay, so our goal is to have as less assumptions as possible. But the first real assumption that we do, we think that electromagnetic radiation is a classical radiation. So hence, we solve Maxwell's equations. So we look at the electrodynamic part, and we solve fully vectorial Maxwell's equations on the grid, depending on the geometry, using so-called finite difference time domain technique on the parallel supercomputers. Now, to couple electrodynamics with quantum emitters, we solve Liouville-von Neumann equation at every grid point where we assume the quantum emitters are. And we calculate the polarization, and time derivative of the polarization enters Ampere law, and we solve this whole thing self-consistently using home-built codes. There are several assumptions made here. One of them, of course, as I mentioned, electromagnetic radiation is considered to be classical, so our intensities have to be relatively high to make sure that this is related to experiment. Number 2, every grid point occupied by quantum media is associated with a polarization density driven by a local electric field. So this local electric field is taken from Maxwell's equations, and we calculate polarization, plugging it back, and so on and so forth, self-consistently. Multiplication of the average dipole moment by the number density of emitters at a given point is equivalent to mean field approximation, of course. Now, but mean field approximation is only within a single grid cell, which means that the grid point to grid point interactions are all included in terms of, so if you have a quantum meter here, they will radiate the radiation that is taken into account in Ampere law, and this whole thing is included in this scheme. Now, you can do much better than mean field. Of course, you can include Lorentz correction term, and I'll show you in a second. Now, the total density matrix of the wave function of the system is a product of individual wave functions, which means that we neglect static emitter-emitter interactions. So, and finally, local field correction. You can include local field. This is the part from the Maxwell's equation. This is the local polarization, macroscopic polarization. So you include dipole-dipole interaction within a single grid cell. So that's the end of sort of setting the stage. Now, one important thing to realize, even if you want to work with a very simple two-level system, and if this two-level emitter sits next to a nanoparticle, and nanoparticle is illuminated by external radiation at the plasmon resonance, the scattering is so strong that at a given point you can have any polarization possible. So the polarization changes with time and with the spatial coordinate, which means that you have to include all possible projections of electric field on the laboratory system of frame, which means that your two-level emitter is not really a two-level emitter in 3D. It has all 3 sub-levels, and we take that into account, of course. Right, and now we have working codes with the 3 levels, and we have also diatomic molecules with vibrational rotational structures included. Yes?
Do you have separate pumping for these systems? I mean, are they optically pumped?
I'm not sure. I understand what you're asking, but I'm not sure what is, what sort of answer you're. So we have external field that drives the system. That will be my answer.
Right. But,
which is, as a, let's say, as a plane wave coming into the calculational grid.
But I think this becomes really interesting when there's some additional laser sources which are pumping the system, and maybe looking at some possibility of gain?
Yeah, yes, of course. We do have it. And we could have a really long conversation how this pump should be included. And in reality, of course, what you do in the real lab, you have real pump that's pumping the system. In the standard theory, what you have is tiny small number sitting in the equation that they call it pump. So what we do, we looked at the both possibilities. So we include external pump as pumping the system, look at the possible lasing, and we also compare that to the phenomenological number that sits in the block equations. Okay, so we have both. Okay. All right, so first very simple example, if you look at the very thin layer of interacting quantum emitters, you shine the light through, and the intensity of the light is low enough such that we look at the only linear properties of the system, one photon absorption, transmission, or reflection. You can look at the absorption as a function of the wavelength, and if you consider these molecules at two-level emitters at 1.6 electron volts and calculate the absorption at different densities, what you will see a very nice Lorentz shift. So this is the low density, intermediate density, high density, and you have a very nice Lorentz shift which goes as it should with the energy and the density as predicted by theory, of course. Okay, now the first test is for the theory is to try to explain that third resonance feature that I mentioned a few minutes ago. So what we want to look at first, let's take a look at the very simple exercise as an exotonic cluster. So the cluster that is comprised of interacting emitters with no plasmons yet. So each emitter is a two-level emitter, of course with all the three levels taken into account in 3D, such that the energy transition is on the order of 3.1 electron volts. So at very low density, what I assume, if I launch the plane wave and look at the, let's say, scattering, what I will see is probably one resonance at least at 3.1 electron volts. Now, if the density is high enough, of course, there will be collective effects. And my interest is to see what sort of collective effects I will see. So what he's looking at is the scattering as a function of the incident energy, the energy of the photons, at three different densities. There is a tiny small resonance pretty close to this 3.1 electron volt that corresponds to the transmission energy. But there is a second resonance that increases its intensity as the square of the density, suggesting collective nature of this resonance, and it's insanely broad. But so when we published this paper, we were trying to publish this paper, one of the referees said, well, this is the super radiant mode. Well, I beg to differ, because this is the classical electrodynamics. We don't have photons per se, so I would really hesitant to say that this is a super radiant mode. But it's certainly a collective effect because the intensity scales as the square of the number of density. So we can have a long conversation over coffee, try to discuss whether this is a super radiant mode or not, but I don't think it's a super radiant mode because we solve Maxwell's equations classically. Okay? So you have two modes. One of them is a surface mode, the mode associated with individual emitters emitting the radiation not in collective way. And of course you have this quote-unquote super radiant mode, but the collective mode, with all emitters emitting in the sort of resonance, and the entire particle basically shines at this particular frequency. Okay.
Why is it blue?
Good question. So this is the collective mode, which means that the energy of this mode is higher than the energy of the individual emitter. All right. So now combining the excitons with plasmons, we look at the core shell particle. So core is comprised of silver and the shell is comprised of our emitters. So here, bear with me here. So first of all, if the density is really low, we're looking at the scattering as a function of the frequency again. If the density is very, very low, what you have is a nice Rabi splitting. Okay? But when the density becomes higher, higher, and higher, the splitting becomes greater, and the third mode appears. So this third mode scales again as the square of a number of density of emitters, suggesting collective nature as well. And we'll talk about it more in a few seconds. Okay? So the core shell particles exhibit strong Rabi splitting with the third resonance sitting right in the middle and scaling as a square of a number of densities, suggesting collective nature of this resonance. If I turn off my core, what I will have is a single strong resonance. And of course, if the density becomes higher and higher, we'll have these two resonances we just talked about. But when the plasmon particle appears right in the center, it creates this nice Rabi splitting, and the third resonance is really, really popping up from the scattering intensity. Okay? So let's take a look at the periodic array of slits covered by the thin layer of quantum emitters. So first, we have a transmission as a function of the energy, and this is the solid line, and this is for a periodic slit array without any emitters at all. So we have a nice plasmon resonance. Now, if you bring a thin layer of emitters with no slit array at all, so what you have a nice absorption feature right here. So you adjust parameters such that the plasmon resonance sits right on top of the absorption feature. And first, what we want to look at, whether we have a strong coupling. And if we do have a strong coupling, we try to increase the density of emitters and see whether we have this third resonance appearing in the system. Okay? So here's the first simulations for low molecular densities. For the low molecular densities, this is transmission as the function of the energy in electron volts at different periods of this slit array. So what you see is a very nice avoided crossing picture, as it should be. So if you trace the position of these energies as a function of the one of the period or the wave vector, what you will see is the upper polariton, the lower polariton, nice, very nice avoided crossing. Okay. Now you can use, instead of doing these hardcore simulations, you can use a simple 2x2 matrix model, diagonalize that, and these numbers fall right on this very nice model the calculations. Right. Now, so now I'm cranking up the density, and the Rabi splitting becomes wider, wider, and wider. And what we see is the appearance of the third mode. So if the density is really high, this third mode really pops up, and it's very, very narrow and very strong. Now, again, this is transmission as a function of the energy at the high densities. Different curves correspond to different periods. So basically, I'm sweeping through this avoided crossing picture just to see where the coupling occurs. Right? Again, so this is the energy of upper polariton, lower polariton. And this is the energy of my third mode that is nearly disperseless. But what happens is that it actually repels the upper polariton at high periods. Okay? So the result of high molecular concentration reveals the third mode here. And this transmission, by the way, has nothing to do with the absorption, as one may naively think. The transmission has a maximum, which means that this is not an absorption of the molecular layer. It has something to do with collective nature of these quantum emitters interacting with plasmons. Okay. Now, in order to prove the concept of collective nature, we have a magic knob in the code that can turn off molecular-molecule interactions, keeping intact molecular-plasmon interactions. So basically, assuming that the entire thin layer of this quantum emitter is a huge quantum dot. Okay, with a single huge dipole. Now, if this mode has anything to do with the collective interaction, then the third mode should disappear if I turn off this interaction, right? But Rabi splitting should still be there because my molecules still interact with plasmons, right? So that's what we do. So this is a transmission as the function of energy for the complete model where everything is included. So you have these three resonances. Lower polariton, upper polariton, and this third magic mode, right? And then I turn off the interaction in molecules and changing the density, i.e., in this particular case, this density would scale to change the dipole of this huge the quantum dot, right? So what you see is that we still have the Rabi splitting as it should, but the third mode disappears. Okay, so to summarize this part is that we show that this third mode appears and it has collective nature. And is actually plasmon-mediated molecular interactions that is expected in other systems where molecules interact strongly with propagating plasmons, and has been seen in several experiments as well. Okay. Okay. So now here's the favorite part of my talk, and unfortunately Misha left, so which means that I'm going to send him email. So too bad for him. So what I would like to show you first is what I don't want to talk about. That is coupled oscillators. You can do it at home. You have 3 bare magnets and place one magnet right in between those 2 and tap the other, and you will see how the energy will start to oscillate between 2 coupled oscillators, right? So you there it comes, and then you tap it. You see the energy starts oscillating between these 2 guys, right? Nice the coupled harmonic oscillators, okay? So there are several experiments. The real pioneer in looking at transient spectroscopy in hybrid systems is Christoph Lee, now from Germany. So he's been doing this tapping of J aggregates with a femtosecond laser, but femtosecond laser is not strong enough to change the coupling, but it is basically providing additional photons such that one of the oscillators starts to oscillate. Since it's coupled to the other one, the energy flows from one mode to another, right? That's what I don't want to do. What I really want to do, I would like to try to control the energy flow between the modes, hybrid modes of the system by tapping the system so strong such that the Rabi frequency changes. Okay? So what I'm going to look at as a transient spectroscopy, sending a strong pump pulse, strong nonlinear pulse with a high enough intensity, and I'm going to probe the system as the pump pulse pumps the system to see how the optical properties of the system change as a function of the pump probe delay, right? But my, of course, probe pulse is low intense enough not to disturb the system. So what, for example, if I look at the periodic array of slits, I would look at the transmission or reflection as a function of pump probe delay when I'm pumping the system very, very strongly. Or core shell particle as well. Okay? So I'm not going to talk about collective mode yet. We are in the process of trying to understand what happens if the density of these emitters is high and I pump the system. So we don't have a really good understanding what's going on. So first I would like to share with you the results that we have for low densities when we have only upper and lower polaritons only. Okay? So here is a transmission reflection spectrum. So the reflection spectra, the red line, is a function of the frequency at a given period and the given density, exhibits 2 really nice dips, upper polariton, lower polariton. And the emitters level diagram here, since it's a two-dimensional structure, you have to take into account m-1, m+1 states, right? So these are right here. And the energies of this state correspond to the surface plasma on polariton. It's really, really broad, of course, right? So the linear transmission spectra has its Rabi splitting, and it's on the order of 75 millielectron volts, relatively high coupling. Okay, so now what I'm doing, I'm pumping the system with a femtosecond 15 femtosecond pulse with intensity high enough such that the population of my emitters inside this pulse is non-zero. Okay? So I have really Rabi cycling. So if I do this femtosecond excitation of a single emitter, I will see this really nice Rabi cycling. Okay? Now, and of course, my femtosecond pulse is not long enough, so I won't have thousands of oscillations. I will have 2, 3 oscillations, something like this, right? So then, here I'm looking at the changes of reflection as a function of the pump probe delay and the energy of the photons. So this is the central line, is the line that corresponds to the absorption energy of my emitter. Okay? This is the energy of the upper polariton and the energy of the lower polariton. So if you look really close enough, unfortunately colors are not bright enough, you have really nice oscillations of the energy between upper and lower polariton. But what really happens is that upper lower polaritons, their population decreases in phase, and the population of the molecules in the excited state increases. So the energy flows like this. Okay? So if you look at this two-dimensional picture with cuts, this is the change of reflection as a function of the pump probe delay for upper polaritons, lower polaritons, and emitters. You see they oscillate out of phase. So the energy flows from one state to another and back and forth. Now, so the energy oscillates between hybrid modes and emitters on the femtosecond time scale. Now, if you increase the duration of the pump, of course, you will have more oscillations. And so here is the oscillations of the upper polariton. And on the same scale, I'm plotting the average population of my emitters as a function of pump probe delay as well. So you see there's a really nice correlation. So my emitters are excited to excited state, and the upper polariton changes, the population of changes, and so on and so forth. Now what's important to realize is that the oscillations here actually faster than the theory would predict. And this is simply because the local fields are strongly enhanced by plasmons, which means that the local field that determines the local Rabi frequency, that determines these oscillations, is driven by the plasmons, and the local field is greater than the incident field. Okay, it's a very simple explanation. So now another thing to note here is that the decay is actually faster than those decays we have in the theory. And to understand why that is, I would like to show you one simple demonstration. So what I'm plotting here, this is the layer of my emitters. The red color corresponds to emitters in the ground state. Then I will turn on my femtosecond pulse, start pumping the system, but you won't see the electromagnetic radiation. What you will see is the change of the color of emitter, which means that given emitter, the given pixel undergoes Rabi cycling. Okay? So this is this part right here. So my radiation comes from the top, comes through this layer, excites my emitters, and of course, due to lightning rod effect, you have a really strong enhancement of the field near the sharp corners. So the emitters that first undergo Rabi cycling will be those that are really close to the sharp corners right here. And this is the time in femtoseconds. So I'm turning it on, and I'm watching the field coming in, building up enough intensity. So these emitters undergo Rabi cycling. Now they're already back to the ground state, while the others are still undergoing Rabi cycling again. So you see a really nice wave packet of quote-unquote excitons traveling, right? And so on. Now, because of this really strong and homogeneous excitation, average populations are not the same as the local populations. Hence, this decay is much faster, okay? And so on. Of course, this is the end of the pump, and the system will gradually decay to the ground state, and so on and so forth, okay? Okay. So here is the final part of the brand new results. So let's take a look at the core shell particle with emitters surrounding the core comprised of silver. And I'm looking at the low density such that I don't want to deal with yet. Don't want to deal with collective mode. We're still working on that. We have no really good understanding of physics there yet. Now, so we have upper and lower polaritons. The density is low enough such that there is no collective mode, but it's high enough to see the Rabi splitting. And I would like to pump the system with a femtosecond pulse and look at precisely the same dynamics. But in addition to that, I would like to use chirp pulses to try to control the oscillations of the energy that go from one polariton to another and so on. Okay? So, and I do that. I have a 90 femtosecond laser pulse, and I'm plotting the scattering as a function of the pump probe delay for the lower polariton here. You see these oscillations of the Rabi oscillations, but they decay so fast, much faster than any time scale that I have in my code, which means that the excitation is insanely inhomogeneous. Now, and also I plot the population, average population of the emitters, and you see that they, of course, undergo Rabi cycling and so on and so forth, and they quickly decay. But energy still oscillates in the femtosecond time scale as well, right? Okay. Now, here's the simple idea. So if you look at the energy diagram of the system that I have, so I have upper polariton. Of course, it's not a single level, but some sort of a band because it has a width, right? So I have a lower polariton as well, and I have a tiny small molecular state right here, okay? Now, let's say I have a chirp pulse, and I'm going from low energies to higher energies sweeping through this energy diagram, okay? And I would assume that if my chirp is long enough, since this system is not really symmetric, going from here to here is not the same as going from here to here. So I would assume that the negative chirp will give me different result as the positive chirp. Okay? And indeed it is the case. So here is the average population, the lower polariton scattering as a function of the time delay between pump and probe. For no chirp, this is the blue line. Positive chirp, green line, and negative chirp, red line. What you see is very interesting, is that the positive chirp gives you control over the period of oscillations of the energy that going between upper and lower polaritons as well. So basically what really happens is our hand-waving understanding is that you have a population trapping going from, this is positive chirp, from lower energies to upper energies. So you're basically stuck somewhere here. Okay? All right. So if you look at the average populations at the different chirps as a function of time, so I'm averaging over all ensemble. And what I see is that you have, of course, Rabi oscillations, but the system decays really, really fast. Now, if I look at the local population, let's say I pick the point here and calculate the population of 1 meters at this point, what I see is that the decay is not as fast because I'm not averaging of the entire ensemble, and positive chirp and negative chirp give me different results. So I have different number of Rabi cycling. Okay? So instead of looking at this point, you can take a look at that point right here. And the situation is completely different. So the negative chirp and positive chirp are basically interchanged. So in reality, imagine that the plane wave comes from the top and is oscillating back and forth, different points excited differently. Okay? So this is the last slide. And it's way too much information, but there is only way I can deliver that. So again, I'm plotting the same populations, local populations. Red color corresponds to the emitters in the ground state. Okay? But I have to plot these 3 examples at the same time such that you will see the difference. So here my pump comes from the top, is horizontally polarized. This is no chirp, just a standard Gaussian pulse. The positive chirp and the negative chirp. Okay? So what I would like you to look at somewhere in the center, so you will see the difference. At the beginning, the dynamics of the order of 35 femtoseconds, everything looks the same. Okay? But after that, the populations will be different. Okay? So here it comes. So the excited, you see the excitation is nearly the same. These guys undergoing Rabi cycling. And now the populations are slightly different. So for example, for positive chirp, the inhomogeneity is not the same as for no chirp or negative chirp, and so on and so forth. Now this, mind you, that this is a 10 nanometer thickness. So that's so you can achieve spatial temporal control over dynamics of this system, okay? And so on. So using, this is the final slide, using self-consistent model of Maxwell-Liouville von Neumann equations, we demonstrated hybrid systems exhibit energy oscillations between hybrid modes, and simulating pump probe experiments, including chirp, we showed that it is possible to control this energy flow. Thank you so much for your attention.
Yeah, I have 2 quick questions actually.
Sure.
Relating to your last slide, I'm not sure I get the geometry. You have linearly polarized light come in
From the top.
from the top. Okay. All right.
So it comes from the top and oscillates back and forth.
Because I was wondering about the asymmetry in the overall field
Right.
that you see between the top and the bottom.
That's it.
Okay, and the other question goes back to the response dielectric functions that you use. It seems like
For metal, you mean?
For metals, yes.
Yes.
A lot of the physics is in there.
Yes.
I've seen the Johnson and Christie paper, and a lot of people seem to refer to the. You said a little more about what you think about those, how accurate they are, and how sensitive the polariton and plasmon motion is to the details that you include or don't in heuristic
So when you solve Maxwell's equations, irrespective of whether you include quantum meters or not, you have to include correct dielectric constant for dispersive material. Right? In this case, it's metal. Now, there are several ways. The easy way is use a Drude model. In Drude model, you have 3 parameters to fit. So, and this, of course, limits to a given certain frequency range where it's valid, right? Now, what we yes, of course. Yes. We assume that our dielectric constant for metal does not depend on intensity. Okay, in this particular. So our intensities are high enough to see the Rabi cycling, but not high enough to change the dielectric of the metal. Now, what we use in our case for epsilon is a Drude-Lorentz model with approximately 18 fitting parameters, such that we cover the entire range of frequencies from 0.5 all the way to 5 electron volts. And it's not only Johnson Christie. I forgot that the other paper recently appeared. It's tabulated as well for the epsilon, so it's more precise than just Johnson Christie.
And those many parameters are obtained by fixed to...
For the epsilon, for real part and imaginary part, yes, that's right.
Absorption.
Yes, that's right. N and K.
Can you go back? You had the slide for core shell, and there was a dip, in the extinction. Yeah, this one. So you refer to these local peaks as upper and lower polaritons.
That's right.
Can I think of this as some sort of a Fano interference between, just the reflectivity of this large core shell and your dark emitters?
That's a very good point. I haven't thought about that.
Because it looks like a pretty typical
At first sight, I would probably agree with you, but I have to think more about that. It's really a nice observation.
What would be continuum?
It's just a broad continuum. So,
yes.
So as you can see, the red line, right, just silver, right? Mm-hmm. It has a very broad spectrum, and then there is a very sharp feature. So it's kind of Fano, but generalized Fano.
Yes.
In terms of chirping, so in a sense, so as understood, you have three-level system, right? In general,
I have
excited states.
I have a ground state and degenerate excited state,
right.
Doubly degenerate excited state.
So in a sense,
in this case, a triple degenerate excited state because it's a 3D. So you have px, py, and pz orbital.
Right, and you are chirping the frequency sort of like from the positive chirp or negative chirp like this.
Right, so it's a linear chirp, right?
So that altogether it's a four-level system in general. Right?
In reality, yes. So,
but you are plotting only population of one of the states, right? I cannot understand why you're breaking the symmetry for negative and positive chirp.
Well, it's because, right, so if you look at the scattering as a function of frequency, what you see is that these guys are not symmetric with respect to the lower energies and upper energies. Now, if you adjust, let's say, the size of the core, you can move plasma resonance back and forth, trying to get this symmetric line shape. If you do that, then the linear chirp, right, then positive and negative chirp will be nearly identical.
So you are cheating in a sense.
No. I'm controlling
you break the symmetry, and now you're telling that positive and negative.
That's the whole idea. That's the whole idea.
Yeah, but this is kind of not fair, right? Okay. Okay.
All right. Okay. Well, if there's no immediate questions, let's thank Maxim again for.